All right, so continuing on with bonding. So we did ionic bonding the other day. So we're going to talk about covalent bonding today. So covalent bonding um, is between nonmetals. Right, so it's between nonmetals. So there's a couple differences. Remember, ionic bonds, we transfer electrons between the metal and the nonmetal. So a covalent bond, electrons are shared, right? It's going to be called a molecule now. So if I have a bunch of covalently bonded atoms, they're going to be called a molecule. And most living things are made of molecules, right? So you're almost all molecules. You don't really have covalently bonded things in your body because most of them would dissolve in water. But you do have ions in your body, and you use those to transfer charge and charge your cell membranes and stuff like that. So rules for covalent bonding, right? So the rules are similar to the rules that we'd have for ionic bonding, right? So electrons are shared, right? So they still do follow the octet rule. So remember we said that all atoms will gain, lose, and then we'll just add or share, right? To be like noble gases. So we can modify that octet rule, right? So atoms. Oh, that's a bad empty. Let me redo that one because I don't like that. So fill our empty. So since all the nonmetals are on the right-hand side of the metalloids, they're all going to share, and then except for hydrogen. So hydrogen can form ions, and it can form covalently bonded. Right. We'll know that they can form single, double, or triple bonds. Remember, ionic bonds are electrostatic attractions, so there's no real physical bond there, but it's an attraction. But these actually form a bond, and they can be rearranged, which is good. So one of the reasons why living things are mostly made of covalent bonds is if I eat an apple, I don't have to look like an apple. I can take all the atoms apart, rearrange them, and put them back together, right? For instance, living things use glucose, right? You use glucose as your form of energy. But if I eat an apple is high in fructose, right? And I can take the atoms in that fructose and rearrange them to make glucose out of them and use it for energy. So that's an advantage. When we name molecules, they're going to be similar to ionic compounds, but different. So I'm going to end everything in "ide." Right, so I'm going to use Latin prefixes. And I'm going to end in "ide." All right, so I'm going to use Latin prefixes and end in "ide." The only rule is mono. Not using the first atom. Okay, so if I look at this first one, I got mono. I got one nitrogen and one oxygen, so I say nitrogen monoxide. Right? I wouldn't say mononitrogen, right? So I don't use mono. Next one, I have one nitrogen, two oxygen, so I'd say nitrogen. Right, so this was mono because there's one dioxide. Here I have two nitrogens and three oxygens, so now I'm going to use that di in front of nitrogen because I have more than one, and then trioxide. Right, I have 2 and 4, so dinitrogen tetraoxide. 2 and 5, so I have dinitrogen pentaoxide, and we can keep going all down. So pretty easy. The thing I'll warn you about, once you start doing this, right? Once you start doing this and you start to see something like this, right? Some people are going to want to go, oh, this is dicalcium trinitride. And it's not, it's just calcium nitride, right? So make sure if there's a metal involved, right? If there's a metal involved, you don't use the prefixes, okay? So if there's a metal, you don't use your prefixes. So just make sure you remember that and you'll be fine. So anyway, let's go into bonds a little bit. So ionic bonding, we can form single, double, and triple bonds, right? So if we think about our periodic table, and you should probably have yours out. So group 1, I have hydrogen, right? So I have hydrogen in group 1. And it only has one valence electron, right? So if I'll do my Lewis dot here, and I have hydrogen, and I have one electron, and I have another hydrogen, and one electron. These hydrogens will want to share this electron because hydrogen wants to be like helium, right? And helium has those too. So hydrogen will share these electrons here, and then once it shares them, we'll draw a single line, and that single line means a covalent bond. So if we look at here, we have 1 phosphorus and 3 chlorines, right? So chlorine has 7, it wants 8, right? So it'll attempt to share. Phosphorus has 5, but it wants 8. So if it shares these, right, then chlorine will have 2, 4, 6. This chlorine will have 8, but this phosphorus will now only have 6. So it wants to continue sharing its electrons. And when it does, it'll form something like this over here. So if I do this in a Lewis structure, remember the single lines mean shared. So now each chloride has 2, 4, 6, 8. They get to share the electrons between them. This phosphorus now has 2, 4, 6, 8. Right? So they all have 8. So all of them have satisfied the octet rule. If I was going to pronounce this, right, I'll pronounce the most electronegative atom first, which will be my phosphorus. So this would be phosphorus. Right, trichloride. Right, so that's what and again I use my prefix here, and I didn't use mono here because we don't use it on the first atom. Right, so double bonds. Right, so we can make covalent double bonds. Now there are 4 valence electrons, right, or 4 valence orbitals. So if we think about phosphorus up here, right, so we had our S, we have a p orbital, and these unshared electrons occupy another p orbital, right? So we have our 4 valence electrons, our 4 valence orbitals, excuse me. So in double bonds, right, so sometimes electrons need to be rearranged, right? So I'll share 2 sets of them in the middle in order to get 8. So when oxygen shares these 2 in the middle, it has 2, 4, 6, 8, and 2, 4, 6, 8. So each of them have 8, right? And the way that looks is, I'll give you an example with this over here. So this oxygen wants 2 more, and this carbon wants 4 more, right? So this oxygen and carbon will share this one, right? And this will share this one here. Now when it shares that, this oxygen over here on the left has 2, 4, 6, 7. This oxygen on the right has 2, 4, 6, 7, right? Because it gets to claim both of them, it shares. And this oxygen here will have 2, 4, 5, 6. So this will actually move this to this side, right? So it'll move it in between, it'll share that one, and this one will move to share that, right? So when it moves them, I end up having this, right? So I have C, O, I'll draw my straight lines, and then I have these place here. Now, if I was going to name this, I would name it carbon, because we'll name it after our central atom. And then I have 2 oxygens, so it would be carbon dioxide. Remember, I use the di because I have 2 of these, and I only have 1 carbon, but I don't use the mono. Okay? All right, so we can form triple bonds, right? So just like we saw with oxygen, right? Sometimes we have to move, right? So if we look at this one here, we can go ahead and share these ones. But if I only share that one set there, I'll have each nitrogen will have 2, 4, 6, right? So it needs 2 more, so it'll share these ones, right? And then it'll share a third set in the middle. And when I do that, I get this structure over here. We'll draw these with straight lines here. There'll actually be 3 lines, like I have down here, right? And that now has 2, 4, 6 in the middle and 2 on the outside, which makes 8. I'll show you one more example over here. Hydrogen cyanide, right? So the same thing. These will share the one here. No, hydrogen wants 2, right? So I've got my 1 bond here. I've got 6 electrons in the middle. So I'll have 3 bonds there, right? And then I have my 2 unshared pairs on the outside. So this nitrogen now has 2, 4, 6, 8. This carbon has 2, 4, 6, 8. And the hydrogen just has 2. So it'll reach octet that way too. All right. So important things to remember, and you'll get more practice doing the Lewis dots, is that single bonds share 2 electrons, double bonds share 4, and triple bonds share 6. Right. So, however you're going to arrange your electrons in your covalently bonded atoms, you have to make sure that you satisfy the octet no matter what. Right. Okay. There are things called coordinate covalent bonds. So in each of the instances I showed you, each atom is sharing electrons. But sometimes atoms need to share both of their electrons in order to become more stable, right? So if we look at this example here of ammonia, right? So coordinate are shared by a single atom. Move this over a little bit, right? So coordinate covalent bonds, right, are donated by a single atom. So if you look at ammonia here, so ammonia molecule, right, is an octet because I have 2, 4, 6, 8, right? But it's next to a hydrogen ion, and a hydrogen ion is very reactive, and it makes everything unstable around it, right? So this nitrogen will share both of its electrons with hydrogen. And when it does, I end up with bonds here, but I retain the positive charge because I'm missing an electron, right? So hydrogen had a positive charge coming in, and this ammonia was neutral, so I retain that positive charge going out. So this is called the ammonium ion, right? And I do have a coordinate bond there. To give you another example, right? There we go. Give another example. I've got boron trifluoride here, and I've got ammonia here. And same thing, they'll come and bond together, and ammonia will donate its 2 electrons to bind boron. Now, boron it's one of the exceptions to the octet rule because it's a metalloid, right? So it really only wants 6. Electrons in the middle, right? So, but it will reach octet and have an overall negative charge, making the ammonia overall positive. So they'll cancel each other out essentially, right? And then I'll make that structure. But that's another example of a coordinate covalent bond. Some things I say, other interesting facts, right? Let me move this down a little bit. Unshared pairs of electrons. So unshared pairs of electrons, I've kind of already introduced them a little bit, right? So they occupy a bonding orbital, right? But they're unpaired with another atom or molecule. But they do occupy. So the thing that they do that we're going to talk about next time I talk to you is they add to the polarity of a molecule. Right? So if you think about it like this, nitrogen is more electronegative than hydrogen. So hydrogen has a little bit of a positive charge. Nitrogen has a little bit of a negative charge. But when I have unshared pairs, electrons have much more negative charge. So it makes it even more what they call polar, because I'll get a pole in this direction. These arrows are the way I show direction of charge, right? So this has one unshared pair, ammonia does. Water here has two unshared pairs, and hydrochloric acid here, hydrogen chloride, will have three unshared pairs, okay? And then bond dissociation energy, right? So it's the energy required to break a covalent bond, right? So bond dissociation is the energy required to break a covalent bond. So covalent bonds are pretty rigorous, but we can detach them. What you have to do is remember that as the number of bonds increases, the strength of the bond increases. So if we look at nitrogen as our example on this one, right? We have nitrogen bonded with itself, right? Dinitride, we could call it. It's kilojoules per mole. It takes 160 kilojoules per mole to separate that bond between nitrogens. Right? If I make a nitrogen with a double bond with itself, it takes 418 kilojoules. And if I make a triple bond, right, it makes 946. And the reason why, if I give you an oversimplified, is as I make more bonds, the bond length gets shorter and it gets held more tightly, all right? So it's much harder to break these triple bonds because the electrons are held more tightly between the nitrogen atoms, okay? All right, we'll talk a little bit about formulas, right? I'll just introduce them and then we'll kind of reinforce them later. So there's different types of formulas I can show things in. Empirical formulas, right? So these show reduced ratios. So we usually use these for ionic compounds. Right, so we generally use these for ionic compounds because if I had sugar, right, my empirical formula for my sugar would be C2. Oops, I'm sorry, that is not correct. Right, I'd be C H2O. But this doesn't tell me that anything about that sugar, right? Because that CH2O, and we can put an N outside. It means by any multiple, it could be wood, sugar, lactic acid. It could be a whole bunch of different things. It could be glucose, fructose, lactose, right? So molecular formulas. So these, right? Oops. They list all atoms in a molecule, right? So again, I had glucose, right, which was right here, which is C6H12O6. But you'll notice that's also the formula for galactose and also the formula for fructose, right? They're all the same, but it lists everything in there, right? And that's the most common way that we give formulas. I can have structural formulas, right? This one shows where individual atoms are bonded. So now if I have structural formulas, remember that glucose was C6H12O6, and so is fructose. But when you look at them, there's differences in them, right? I got differences right here, right? And I've got differences right here, right? I've got ethanol group up here at the 1 carbon on fructose, and it's at the 6 carbon on glucose, right? We also have some rearrangement right here of a hydroxyl group, right? So there are some slight differences. So if you had fructose, you can only make energy from glucose. You would send this to the liver, and the liver would take this 1 ethanol group off of 1, put it on 6, and it would flip it around on 4. You have enzymes that would do that for you. And you can make the fructose into glucose, right? So the structural formula shows a little better, right? The ball and stick, right, or spatial. So both of these formulas, so three-dimensional. So three-dimensional we're going to talk about next time we talk. And it really gives you an idea of how things work spatially, right? So for instance, if I had this structural formula for methane, right? So this is our General Lewis structural formula. It shows everything flat, two-dimensionally. But we don't live in a two-dimensional world. So the ball and stick shows 3D structures, right? And we're going to do a lot with this next time we talk. But it shows you the bond angle. So if you think about this, the way this shows here, this shows a bond angle of 90 degrees, right? But the bond angle for methane is much more than 90 degrees. It's 109.5, right? Because that's the way I can arrange these in 3 dimensions, because the electrons and the bonds want to repel each other, right? I got formaldehyde down here. So formaldehyde, right, the ball and stick, is still a two-dimensional because it's what they call planar. It's a flat molecule, but it shows the bond angle of 120. Spatial, right, so the spatial formula here, right, shows atoms in their relative size to each other and how they're attached, right? So different types of formulas, and then we'll continue to reinforce them as we go. That's it for now.